All right, folks, welcome back. It's gonna be the last video I'm gonna make, so it's sad. Can't even believe it. All right, so I told you guys the other day when we did our final exam reviews on Monday and Wednesday, you're welcome to watch those videos again. Highly recommend watching those videos. From class last period, you can find those under conferences in Canvas. And these were the few problems that I didn't get to that I would have liked to review with you. So, and there were also just the couple of concepts that we didn't cover, so I will get to those as well. Wanted to start out with this mixture problem. And so I want to make 170 milliliters of a 36% solution, but I only have 24% and 58% solutions. So I'm gonna, get in my chemistry lab and pour these in like the mad scientist, and I need to figure out how much I need to mix of each. So I need to find how many milliliters of each solution that I need to mix. So whenever you read a story problem and it says this word mixed, you're like, oh, this is a mixture problem. All right, so typically in a mixture problem, I like to think that there's a quantity statement and then what I call a value statement. So the quantity statement is literally going to say, I'm going to have some of this stuff and some of this stuff. And that's going to be total of 170 milliliters. Right, so I have no idea how much of this solution or that solution, but they're not the same types of solutions, so they have to be represented by different variables. So, but it's going to be some of this and some of this going to be mixed together to make that. Okay, and then my value statement is going to be, yeah, but what's the percent times the quantity, right? So I have some 24% solution. How much of that? Well, the value of it, 24% solution. I have no idea. 24% solution times the quantity of the solution, though, is how much of that I will get. And the 58%, which we're going to write again as decimals, times the y is going to give me the percent of this solution. Okay, and then, so again, this is the percent times the quantity, percent times the quantity. So I'm looking for the percent of the total times the quantity. All right, so these are my two equations, and this setup lends itself to substitution. So I'm just going to subtract the x from both sides, and we'll get that y is equal to 170 minus x. Now that I know a value for y, I can just substitute that right here. So we're going to get 0.24x plus a 0.58, and y is now 170 minus x. This 0.36 times 170 is going to be 61.2, and 0.58 times 170 is going to be a 98.6. Okay, so we get 0.24x plus a 98.6 minus a 0.58x, and that's going to be equal to the 61.2. Again, the 61.2 is just 170 times 0.36. All right, so I'm going to combine these like terms and subtract this 98.6 to the other side. And so I'm going to get, this is going to be a negative 0.34x, and that's going to be equal to 37.4. And when I divide this negative 0.34, I'm going to get that x is equal to 110. Okay, well, what does this mean, this 110? This 110 means the quantity, so that's what we said. This is our quantity statement. So x stands for the quantity of the 24% mixture. All right, so x is the 24% mixture because that's the percentage that I attach to x, or the 24% solution, excuse me. And y is going to be the quantity of the 58% solution. All right, so the quantity here is going to be a 110. Well, how do I find how much for y? Well, I'm just going to substitute that into here, and I'm going to say that y is equal to 170 minus 110 because that's the value for x. So y is going to be equal to 60. So we will put in 60 milliliters of the 58% solution and 110 milliliters of the 24% solution. All right, so that is the mixture problem. Again, you're going to go with just a straight up quantity statement. X plus y is equal to that, whatever it is, the total. And then you'll have a value statement, and these will be either percentages or, it'll be like a mixture of nuts that costs, you're going to put raisins and you're going to put peanuts, and then the raisins cost, $3.21 a pound, and the nuts cost $5.29, and you want to make a 50-pound mixture of $4.20 or whatever the case is. Okay, so those cents would just be attached to each one of these variables, but the quantity, again, would just be like the x plus y is equal to the 50 pounds that you want to make. All right, so that is a mixture problem that goes over systems of equations. Another problem that I want to review is just multiplying polynomials, but when you have several of them, or two or three term polynomials that are being multiplied together. So if I wanted to multiply these together, well, looking at this one, what I'm going to do first is I'm going to just multiply either the first two or the last two or these two. It doesn't matter. So, but I got to FOIL them. So I'm going to FOIL these firsts and say that's going to be x squared. The outer is going to give me a negative 3x. The inner is going to give me a 5x. And the last are going to give me a negative 15. These can be combined, so we get x squared plus a 2x minus 15. But I still need to multiply this result here by the x plus 2. All right, so you could just distribute this x to each one of these and distribute the 2 to each one of these. That totally works. You could also do vertical multiplication, which I'm going to do here because I like it because it makes all of the like terms lined up. So I'm going to start with my 2 here and say 2 times negative 15 is a negative 30. 2 times 2x is going to be a 4x. 2 times x squared is going to be a 2x squared. All right, so I've done the 2, I've distributed it and multiplied it by everything. Now I'm going to move over to this x. When I do x times negative 15, I'm going to put that negative 15x right here because this here is my x column. And then I'm going to do x times 2x, and that's going to give me a 2x squared. That's going to go here in the x squared column. Then I'm going to do an x times an x squared, and that is going to give me x cubed. All right, and now my like terms are lined up in these columns. So I'm just going to bring that on, this negative 30. Here I'm going to combine the 4x and a negative 15x for a negative 11x, and here I'm going to get a 4x squared. And I'm just going to bring down this x cubed because there's nothing to combine it with. So this is the answer to this one. Again, if you had 3-term polynomial, I would recommend lining these up and doing the vertical multiplication. It makes it for a lot cleaner of a problem. Okay, so these are these couple of problems. I've got a couple more stuff that we've covered pretty well throughout the semester. I'd like to do rationalize the denominator. And one that would just say like divide, but they look like the same problem. So this one would contain radicals. And remember that rationalizing the denominator means to get the square root out of the denominator. Okay, so we want no radical in the specified place, which in this case is in the denominator. We could also have, with complex numbers, this would just say divide, but it's the same process. So let's look at this, and we're going to say all right, so dividing radicals or rationalizing the denominator, same thing. So process here is I'm going to look and I'm going to say, hey, I'm going to use this concept of a conjugate. Conjugates are the same two terms. Like if I had x plus 2, there's two terms because they're separated by addition and subtraction. So this is a binomial term, and a conjugate is the same two terms but with opposite signs. So if I had x plus 2, the conjugate would be x minus 2. If I have the square root of 6 minus the square root of 5, then the conjugate would be the square root of 6 plus the square root of 5. Okay, if I have 2 minus 7i, then the conjugate would be 2 plus 7i. All right, so I'm going to use this concept of the conjugate. Whatever I do to the bottom of the fraction, I've got to do to the top. Okay, I'm going to erase my conjugates here. All right, so I'm going to multiply both the top and the bottom by the same thing. And we're using a conjugate here because there are two terms. They're separated by this addition or subtraction. Okay, so we use a conjugate to get rid of or to rationalize the denominator or divide complex numbers when we have two terms. All right, so when I do these first times the first, the square root of 6 times the square root of 6 is just 6. Okay, the outer is going to be plus the square root 30. The inner is going to be minus the square root 30. And these will sum to 0 always when you use conjugates. All right, and then the square root of 5 times the square root of 5 is just going to give me 5. Or negative 5, because this sign here is negative. So 6 minus 5, what's on the bottom here then is literally just 1. When I multiply out these conjugates, I literally just get 6 minus 5, which is 1. Okay, but what am I going to get on the top? Well, on the top I'm going to get the square root of 18, when I FOIL here, plus the square root of 15, plus the square root of 12, and plus the square root of 10. Well, none of these are like terms, but I can simplify this one and this one. This will factor to a 9 and a 2, and this one will factor to a 4 and a 3. So simplifying this, then I would get 3, this 9 comes out, root 2, plus the square root of 15, plus 2, this 4 comes out, square root of 4 is 2, root 3, plus the square root of 10. Since it's all over 1, it's just this. Okay, so that is rationalizing that denominator. What we have here is going to be the same process, which is why I want to talk about these together. If I'm going to divide a complex number again, I'm going to FOIL this bottom here, and I'm going to get 2 times 2 is 4. And the outer, I'm going to get this plus 7i, the inner a minus 7i. And again, these middle terms will always sum to 0 when you're using conjugate. The last here, though, I'm going to get a negative. 7 times 7 is 49, and I'm going to get an I squared. All right, so what do I have left here? If these sum to 0 right here, then I've got 4 minus a 49 I squared. But remember, here, this is what's really important about this one, so pay attention to this one, that the value of I squared is equal to negative 1. So anytime you see I squared, you should be like, I can simplify that further. This I squared right here is actually going to be negative 1. So negative 49 times a negative 1 is really going to give me a positive 49. And I need to add 4 to this 49. So what I get here is 53. Okay, this is what is on the bottom. I have 53 on the bottom of this here. All right, well, what's on the top? Well, I'm going to get 5 times 10, or 5 times 2, which is 10. And I'm going to get 5 times 7i, which is going to be a 35i. So that's the first outers. The inners, I'm going to get a 12i. And the last, I'm going to get a 42i squared. All right, again, I'm going to replace this value of I squared with a negative 1. So that's going to give me a negative 42. So I'm going to have 10, sorry, I ran out of room over there, minus a 42 is going to give me a negative 32. So when I combine these two, I get a negative 32 because I squared is negative 1. Here, I can combine these. A 35 plus a 12 is a 47i. So this is the answer here. So you always write this in the format of a plus bi. All right. So again, this is material we've already covered. Just wanted to review it. It was on my list from the other day, the problems that I didn't get to, and I promised I would post. So hope this is helpful. Last problem that I'd like to do, that's a concept that we haven't gotten to, is an inequality that is an and or an or. So a compound inequality. And let's do that we have a negative 5 times x plus 4 is greater than or equal to a minus, and then x plus 4. And we're going to do 2x minus 7 is less than 15. Okay, remember that this and means the intersection. Or in other words, this whatever solution we find, it has to be where both are true. That it makes this one true, this equation, this inequality, and this inequality. They both need to be true. Okay, so let's just solve each inequality here. And we're going to get, when we distribute here, a negative 5x minus 20 is going to be greater than or equal to a negative x minus 4. I'm going to move the 20 over and the x over here. So those sum to 0 and those sum to 0. So we have a negative 4x is greater than or equal to 16. Now, another rule that we need to make sure we remember when we have inequalities is that if we multiply or divide by a negative, then we have to flip the sign. All right, so we have to flip that sign. All right, so right here, I am going to divide by a negative 4. And when I divide by this negative 4, I have to switch this sign here. So now I'm going to get that x is less than or equal to a negative 4. Great. On number line, what this looks like is we're talking about all the values including negative 4 and everything less than that. All right, so we're looking at all of these values from negative infinity to 4. So if I plugged in negative 5 is less than or equal to negative 4, true. If I plugged in negative 4 is less than or equal to negative 4, true. That's why this is a bracket, it's included. So remember over here, if we have equal to's, we will have brackets. And if we have no equal to, then we will have parentheses for any interval notation that's on the test. All right, so I'm going to add 7 here to both sides. So this is just a solution for this one inequality, but I want to know for both. So I'm going to get that 2x is less than 22. I'm going to divide by 2 and get that x is less than 11. Okay, well, what does that look like? X is less than 11. Okay, I'm going to graph this one here, this solution, the x is less than 11 in this green. So I'm going to say, all right, well, 11 is all the way over here, and it's anything that is less than. Okay, so I have all of this too, and that's going to keep going. Anything that's less than 11, but it doesn't include 11 because there's no equal to, right? So this is going to be a parenthesis here. Now, it's really important to understand the difference between the and the or. Okay, the and is what value would make this one and this one true. Well, if I plug in 0 right here, 0 is less than 11, that makes this one true, but it makes this one false. 0 is not less than or equal to negative 4, so that is not part of my solution. My solution is only the part where they overlap, or in other words, that makes both of them true. So if I were to write this solution in interval notation, I would have from negative infinity to 4 and include 4, because I need to make this statement and this statement true. Now that's if it said and, but what if it said or? Well, if it said or, then I would include, okay, if it said or, I would include these values here and these values here, but not the values on this side, right, over here. Because if I put in 12, 12 is not less than 11, that's false, and 12 is not less than negative 4, that's also false, so this is false here. So if I was looking for or, then I would be going from negative infinity to 11, but not including it, okay, if it said or. But when it says and, it's where they overlap. And that is only this area right here. It needs to be true for both. All right, so that is inequalities. And that is the last bit of the stuff that we already know. There are 4 more concepts that I would like to quickly go over that you need to know for the exam that we weren't able to get to. So I'm going to teach you the short versions of how to do these problems. First one is going to be the distance formula. Okay, the distance formula is basically derived from the Pythagorean theorem that says if I take the length of one side of a triangle, remember this is right angle here, so this is like A or B. So this is a leg, and this is a leg, and this C is always opposite of the right angle, and this is the hypotenuse. Okay, so A squared plus B squared equals C squared is the Pythagorean theorem. So basically, if I take this distance and square it, and I take this distance and square it, then that'll be equal to this distance squared if I have a right triangle. All right, well, how does this relate to the distance formula? Well, the distance formula is going to be equal to, now this is going to seem super crazy, but x1 minus x, or x2 minus x1, we're going to square that, plus y2 minus y1, and we're going to square that. Well, this is because we're talking about ordered pairs. So if I have an ordered pair, so I'm going to draw what this looks like over here. Say like I have the ordered pairs 2, 5, and negative 3, 1. All right, well, I'm just going to graph those real quick so we can actually see what we're doing here. Okay, so 2, 5 is this point right here, 2, 5. And negative 3, 1. Negative 3, 1 is the point right here. Yeah, negative 3, 1. So we've got, oh my goodness, you guys, 2, 5 is right here. Negative 3, 1. All right. Whew, wow, that was really hard. And I'm wanting to know what the distance is between these points. Well, this is why the distance formula is this. Because if I were to say, well, what is the distance in the y direction, right, in the y terms? The distance from here to here is the difference of these y terms. It's 1, 2, 3, 4 units, right? So it's the difference of the 2 y points. That is this here. That's the one side of my triangle right here. And the difference, or the distance between my x terms, which is from 2 to negative 3, is going to be 1, 2, 3, 4, 5. All right, so the distance from here to here is going to be 5, and the distance from here to here is going to be 4. This is my triangle, but without making this triangle with the points, the distance formula is going to give me the distance between here and here. All right, so again, if I plug these points in, my x2 point is 1, or is negative 3. I'm going to subtract my x1 point, which is 2, and I'm going to square that. And my y2 point is 1, and I'm going to subtract my y1 point. Again, I'm just saying this is ordered pair 1, and this is ordered pair 2. That's all this says. All right, so I'm going to get a negative 5 squared here, and negative 5 squared is going to be 25, and a negative 4 squared is going to be 16. All right, so again, we already calculated the distance when I was explaining where the distance formula came from. This is the distance that I traveled in the x direction and the distance that I traveled in the y direction. So as we can see here, that was 5 and that was 4, the difference here. So I'm going to add those together, and I'm going to get the distance is equal to 41, the square root of 41. Well, 41 is prime, so I can't simplify that at all. So the distance from here to here is the square root of 41. All right, so that is the distance formula. Again, it's derived from the Pythagorean theorem, and I showed you the y here. I wouldn't focus too much on the y. You just need to know this formula and that these are subscript for 2 ordered pairs and how to plug them in. All right, so that is distance formula. The next thing I would like to talk about is if we have functions. For instance, we talked about maxes and mins, and how maxes and mins are vertex points. So we have a max if we have a parabola that, you know, opens downward. Then this line right here would be our maximum point, which is at this vertex of x and y. All right, and we can have a min if I have a parabola that opens upward. Okay, and this point right here, this xy vertex here, would be the minimum value. We'll never go below that. This is also related to domain and range. Like the domain will never go above here. The range will never go above here. And the range here will never go below there. So again, this max and min concept. Where we apply this is in, again, with parabolas. But some cost functions in business are modeled by parabolas. So say like I have a cost function that is modeled by a parabola here. All right, again, and these represent, you know, like variable costs and non-variable costs. All right, so, and it'll say here that x represents the quantity of whatever the product is. So say like I'm making bikes. All right, so x represents the quantity of bikes that I would make. Okay, so I want to know what the minimum number of bikes I need to make to break even. The minimum number, sorry, not to break even, but the minimum number of bikes. The minimum number of bikes. Well, the way that I'm going to find that is, again, back over here, the minimum is going to be this vertex value. So really what this is asking me for is, what does this parabola look like? Where is its vertex? Because that's going to give me the minimum amount of bikes. Okay, so how am I going to find this? Well, we've got to go back to our vertex formula. And remember that when you're given a parabola, okay, that the x point is negative b over 2a. This is my x value of the vertex. And how do I find the y value? Well, I plug in whatever I get for this x value right here. Okay, and that is going to be my y value. So you need to know this vertex formula to figure out a cost function problem like this, where it's like, okay, well, tell me what the minimum for x will be. Again, we know this parabola is going to open upward. This cost function is going to look like, you know, something like this. because this is positive. All right, and I'm not factoring this. I'm not trying to find the intercepts or anything. I just want to know what's the minimum that I have to do. Well, I'm going to do negative b. So this is when it's in the form of ax squared plus bx plus c. So negative b, or the opposite of b, is going to be 300 all over 2 times a, which in this case, a is just 1. So I'm going to get a value for the x term right here of 150. Remember that x here told me that x represents the quantity of bikes. Well, that is the minimum number of bikes that I would produce, that I could produce. Okay, so I don't even need to find the y value of this because I'm not asking for like the line. I'm asking for the quantity of bikes, which is represented by x. Okay, so this is a cost function. Again, a real life application of this. Next thing I want to do is talk about logs. All right, so again, this is new material, so this one's new. We've got 3 more new concepts that I'm going to go through. This second new concept, and let's not do logs, let's do exponential functions. All right, so we're going to do exponential functions. Okay, well, exponential functions are written in the general format of, well, it's a function, so it's written f of x, and then you'll have a base to sum to the power of x. All right, so we could have several different things here, and this function can be shifted all over just like a parabola can. Like if I have x squared, then it's just like this, and if I have x squared plus 2, then what that does to this is it shifts everything up 2. And if I have x squared minus 5 in here, oops, x minus 5 squared, then what this does is shifts it right 5. Right, so we've talked about all these shifting, but you don't need to worry about these shifts, okay? All you need to worry about is how do you graph this function. And you're like, whoa, what the heck? I haven't really seen this before. But you do know how to plug in x and see what y is, right? So remember that this is the equivalent of y. F of x is the same thing as y. So I can make, so let's graph 3 things here. 3 exponential functions. Let's graph 5 to the x. Let's graph 3 to the x, and let's graph 2 to the x. So if I were going to make an xy table here, if I plugged in -1, then this would literally say 5 to the -1. Well, that's equal to 1/5. Remember that rules of exponents say if I have a negative exponent, if I want to make it positive, I'm going to put it in the denominator. So we've got this 1/5. If I plug in 0, anything to the 0 power is 1. Great. If I plug in 1, 5 to the first power is just 5. Okay, so I have these ordered pairs, -1 and 1/5, 0, 1, and 1, 5. All right, here, let's do same thing. Let's do 0, 1, 0. Well, when I plug in -1, that's going to be 3 to the -1, which again, I'm just using this rule of exponents. I'm going to get 1 over 3. When I plug in 0, that's going to be 3 to the 0 power. Anything to the 0 power is 1. And when I plug in 1, well, 3 to the first power is just 3. So you can see here then that I have the ordered pairs of -1, 1 over 3, 0, 1, and 1, 3. All right, so let's now do this 2x and plug in the same points. So again, this is a concept that I want to make sure that we're covering thoroughly, how to graph an exponential function. We can do this by plugging in points. If I have 2 to the -1, this is going to give me 1/2. If I have 2 to the 0 power, this is going to give me 1. If I have 2 to the first power, this is going to give me 2. So again, here's my ordered pairs. All right. Now, what I want you to notice is that every one of these graphs, no matter what the base is, the base we changed it, boom, changed it, but it always has the point, you know, we've graphed the point -1, and then in this case, then it's always whatever the space is going to be 1 over that. Base is 3, 1 over 3. Base is 2, 1 over 2. All right, so we have that point, and then we have this anything to the 0 power is 1. So that always goes through 0, 1. So oddly, no matter what the base is, every one of these are going to go through the point 1, 0, and 1. Again, that's without any shifts. All right, so what does this look like? Well, at -1, I'm at 1/5. So this is like really close here. Then I'm going to go through the point 0, 1 and the point 1, 5. This is exponential, and you can see this is going to just take off here. But again, it goes through this point 0, 1. Well, what does this one look like? I'm going to have the point -1 and 1/3. I'm going to have the point 0 and 1, and I'm going to have the point 1 and 3. So again, this looks, sorry, whoops, okay. So this looks the same. You can tell that the base is bigger, it's steeper, okay? And if the base is smaller, then I've got the point -1 and 1/2, the point 0, 1, and the point 1, 2. So you can see that this is less steep. So the smaller the base, the less steep it is. All right, so you just need to know how to graph these exponential functions. Again, you can plug in values for x and spit out y. You don't need to know any more about the way these functions work. But I do want to point out that given whatever the base is, you will always have the points -1, 1 over b. You will always have the point 0, 1, because anything to the 0 power is 1. And you will always have the point 1 and whatever this base is. You can see that pattern down here. So this is graphing an exponential function. All right, so now we're going to talk about logs, which are the inverse of exponentials. Okay, so the inverse of exponentials here, the only rule that you are going to need to focus on and really understand how to do is that log base b to the y is equal to x. And that means that b to the x is equal to y. Now, whether I use y or x here, it doesn't matter. These are just variables. I could use an a and a c or a d and a p. It doesn't matter. Okay, all this says though is that if I have some log, so say like I have log base 9 to the 4x, okay, and that's equal to 1. Well, let's talk about what each of these mean. This b right here is always going to be the base. It's the base when it's in log form, and it's the base when it's in exponent form, right? This here is exponent form. Okay, so this is exponential form. So b is the base, regardless. All right, y here, this y right here is called the argument. Okay, so the way that I remember this is you're just going to switch the x and y. So the base stays the same. So if I wanted to write this in exponential form, then it would just say 9 to the first power is equal to 4x. Sweet. 9 to the first power, again, b to the y is equal to x. So whatever x is now going to be the exponent here. So you need to know how to go from log form to exponential form. And then from here, you need to know how to solve an equation. So, well, I just want to know what x is. I'm going to divide by 4. That means that x is the value of 9/4. Great. Not a problem. Let's do another one. Let's say that I have, I'll do it over here, a log base 5, and the argument here is going to be 3x plus 1, and that is going to be equal to 2. Well, I want to solve this, but with the log in there, that's not going to do me any good. I can get rid of the log by writing this in the exponential form. So the base, again, this is always the base. So I'm going to say, all right, well, 5 squared, because I'm going to swap these two, is going to be equal to 3x plus 1. Not too bad. Well, 5 squared is 25, and I know how to solve this equation. Once you can get from log form to exponential form, you're good to go. You're golden. This is exponential form right here. We can solve this. I'm going to subtract 1, get 24 is equal to 3x, divided by the 3, and x is going to be equal to 8. Okay, piece of cake, once we get it in this exponential form. All right, so let's do one more. Let's say that log base, let's do a 36, and let's do 5x minus 4 for the argument, and it's going to be equal to, and then let's do 1/2 here. All right, so again, this is ugly. I don't know, the log makes me feel uncomfortable. I mean, I don't know, you can think, ooh, if I see log, that's crap. No, I don't know, it's not poo. But if I had had the chance to teach these in class, believe me, we would have had a lot of fun with this. Anyway, I'm going to write this in exponential form. This is going to be 36 to the 1/2 power. It's going to be equal to 5x minus 4. A lot of people get hung up right here because they're like, oh my gosh, I don't know what this means. Yeah, you do. Because remember that any radical is a rational exponent. So this is just going to be the square root of 36, which is 6. So 6 is going to be equal to 5x minus 4. I'm going to add the 4 to both sides. 10 is equal to 5x, and I'm going to divide by 5. Sweet. X is equal to 2. Piece of cake. Again, I can solve these real easy if I can get them to the exponential form. So you are going to need to memorize this information here for the final. Very important to understand how to go from log to exponential form. All right. Last thing here that I wanted to talk about is another application of we don't want a finale, we want a final review, right, exponential form. Okay, so we're going to use this equation, and this equation will be given to you. Whatever equation you need to use will be given to you. But I'm going to explain what this equation is. This right here is going to be your ending balance, or your future value. Okay, so we'll just call it the end balance. This right here is the principal, or your initial amount. Okay, R stands for the rate. The rate will be given to you in percent, and it's always going to be percent annually. Okay, but the way I'm going to write the rate is always going to be in decimal. Okay, N stands for the number of periods that are going to, we'll call these number of compounding periods. Okay, so number of compounding periods in a given time. So if I say, well, this is going to compound, say, quarterly, then this compound, or this n, will be 4. If I say it's going to compound monthly, well, in a year's time, that's going to happen 12 times. If I say daily, this is going to happen 365 times. So this is literally the value for n that you would plug in here and you would plug in here. Okay, t is always time in years. Okay, so what will this problem look like? Let's say that we have $800. We have $800. And we want to invest that at a 4% rate that compounds monthly. And I want to know how long until it is, give me a second. All right, so I want to know how long until it will be $1,020. Okay. So how long until it will be $1,020? What's important here is that you know how to plug everything into the equation that you will be given. This is the equation that you will be given. So the ending amount that I'm going to have is 1,020. Okay, and that's going to be equal to the principal, or the initial amount. Well, that was what I had here, was this 800. And then I'm going to have 1 plus the rate, which again I'm going to write in a 0.04, all over the end. Well, it says monthly here, so the n is going to be 12. And that's going to be a 12 for this end. These are the same n. And I don't know the time. All right. So let's say that I have these different values over here. Let's say that I have that it's going to be 10.1 years, or it's going to be 3.8 years, or it's going to be 6.08 years, or it's going to be 7.42 years, or E is going to be 4.91 years. All right, so again, if I can plug all of this into this formula here, we would typically take a log and do different things to solve for t here, but we don't know how to solve for t. So what we're going to do is we're going to reverse engineer this by plugging in each of these values and seeing what we get. Okay, so how do I mean? What do I mean? Okay, so I want you to watch carefully as I do this. Okay, so what we're going to do, oh my goodness, is we are going to start, and I'm always going to do inside of here. So I'm going to start with this. I'm going to say 0.04 divided by 12. Okay, and I get that like 0.003. Now I'm going to add the 1 to it, order of operations. Okay, so inside of here, I get this like 1.003 repeating. Okay, but I'm not going to round this or anything. And then I'm going to raise this to the 12 times, well, in this case, we're going to do 10.1. Well, 12 times 10.1, so let's calculate what that is. 12 times 10.1. That is going to be equal to 121.2. So this is going to be, 12 times 10.1. Oh my goodness, 10.1. So this is going to be this 1.003 repeating, raised to the 121.2. All right, so here we go again. I'm going to take 0.04 divide it by 12. You always start with the rate, divide it by the n, add it to the 1, order of operations, and then we are going to raise this to the power of 121.2, 121.2. Oh shoot, let me go back here. Let's calculate this answer here. Get the equal to, and then raise it to the power of 121.2. Okay, so this is what we're going to get. So we get this like magic number of 1.496, and again, we're not going to round this, we're not going to do anything to it. What we're going to do is we still have this 800 here that I'm going to multiply by, so I'm going to times by 800 and see what I get. Well, this is giving me, this rate right here, or this amount of time is giving me $1,197.44. That's not 1,020. So let's do this again. But this time I want to plug in 3.8. So I'm going to be smart this time, and I'm going to calculate 12 times 3.8, and we're going to get 45.6 is what we're raising this to. So how do I calculate this? Well, I'm going to take the rate, which they gave me, which was 0.04. I'm going to divide by the 12, because it's going to compound monthly in this case. And then I'm going to add that, add that to 1, this one right here, and see what that equals. So I've got this 1.003 repeating again. Now I'm going to take that result and I'm going to raise it to the 45.6 power. And I get like some number that I have, again, no clue what this number means per se. I just know that if I take anything and times it by something bigger than 1, it's going to be bigger. But I'm not going to round this or anything. I'm just going to take it exactly as is and times it by this 800. And I'm going to get, okay, when I've waited this much time, I'm going to have $931.09. Well, that is also not this $1,020 that I'm looking for. So let's try the next one just for practice. I'm going to do 12 times is 6.08. And that gives us 72.96. So again, going through this process again, I'm going to take, so how did I get this 1.003? I take the 4%, divide it by the 12, the monthly, which is right here. See what that equals, add it to the 1, and that's where I got this 1.0 with the 3 repeating. I'm going to raise that, let me go equal to first. There we go. I'm going to raise that to the 72.96. The 72.96 is the 12 times this time frame right here. This is the time, times the 6.08. Okay, so the 72, I'm going to raise this to the 72.96. And again, this spits out some number, 1.2748. You do not round this number, just leave it in there, times it by the 800. And lo and behold, here we get this 100 and, or this 1984, which this again rounds to, it'll say something like rounded to the nearest dollar. This is going to round to this right here. So the answer at the time is that it would take me 6.08 years to get that $120 that I was wanting. So you're going to reverse engineer this by plugging in these into the value of t into this equation. All right, so that is everything. Good luck on the final, guys, and thank you so much for a great semester. Can't wait to see you all, and definitely have a get together to celebrate your accomplishments and just being a great class. All right, well, I'll talk to you later.